Welcome back to the beam deflection class. So in the beginning of this beam deflection, we try to discuss about one method, that is double integration method. Okay, so today we'll be dealing with the moment area method. So let me go to the moment area method. So by the name of moment area method, you can easily understand there will be the area of moment. So area of moment where we can get from the moment diagram. So what do they say about this method? Another method of determining the slope and deflection. So we can easily identify the slope of the curvature or the elastic curve, right? And we can also find out the deflection, that how much deflected it from the previous or original neutral surface. So in beam is the area moment method, so which involves the area moment diagram. So definitely we can say we need the moment diagram. Just for an example, if you consider a load in a simply supported beam, so what is the moment diagram for this? We all know, if it is simply supported beam, the moment diagram would be look like this, right? Do you understand? If it is a load, the moment diagram would be look like this. So here you can skip the shear force diagram, you can directly draw the moment diagram. I hope you guys are expert enough to draw the moment diagram. So to calculate the deflection and the slope of this moment diagram, slope of this deflected elastic curve, they consider two theorems. So first one they use to calculate the curvature. So what is that? The change in slope between the tangent drawn to the elastic curve. So before I discuss this theory, I should discuss one situation here. Suppose consider this is a beam. Can you see the beam? And which is having a simply supported. One is R1, another is the R2. Okay, there are two reactions, and there is arbitrary loading. So due to this loading, maybe this is the moment diagram. Okay. Now from this beam, you can see initially before applying the load, the beam neutral axis might be in the neutral surface of this original beam locations. But once you apply the load on this beam, it might show some deflection. Maybe this is a deflection curve they are showing. Can you see the deflection curve? So from this deflection curve, they select 2 points. One is A, another is B. And have a look. The angle between these 2 points should be theta AB, because you are drawing the tangent from A and drawing the tangent from B. So angle between these two is theta AB. So that's why they are saying the change in slope between the tangents drawn to the elastic curve. So this is the elastic curve, right? So they drawn two tangents from this elastic curve at any 2 points. At any 2 points, it can be here, it can be here also, because elastic curve is also here. It's also here also, right? It can be here also. It's up to you. You can consider any 2 points. Okay. Is equal to the product of, is equal. So they are saying theta AB, right? So between between A and B, that is, we consider theta AB is equals to the product means what? Multiplication, right? Product of 1 by EI multiplied by the area of moment of diagram between these 2 points. This is important. So you are considering theta AB, this one equals to 1 by EI. So EI is the flexural rigidity, and area between AB, or area between these 2 points. So we consider two tangent points, one is A, another is B. So we know due to this loading, we will have a moment diagram. So from this moment diagram, if you consider the area between these 2 points, that would be a considered area for this. Okay, so what is the value of area here? We'll put here. So what is the main technique you need to know here? calculate this theta AB. Main technique is to draw the movement diagram and get the area of the movement diagram. That is the main challenge here. Rest of the things is easy, right? Because E and I, these are the properties of the materials. Usually you will given this information, or you can decide. Now come to the second theorem. Second theorem is used for finding the some sort of distance, vertical distance from tangent to the point. Suppose if you consider point A, right, and you consider another point B, so you draw two tangents from A and B. So now have a look. A to vertical distance to the tangent of B, this value we consider T A by B. So from tangent, so from the elastic point B to the tangent of A, so this vertical distance or perpendicular distance we consider T B by A. Do you understand? This one we are considering T A by B because we consider the elastic curve point A to tangent B. This is T B by A because we are considering elastic curve point B to tangent A, right? So if I draw a new tangent from here, suppose this is C tangent, because I consider this point is C and this point is another tangent, that is D, just for an example. Okay, so what would be this value? Who can tell me?
Sir, T D by C.
Very good, T D by C, because we considering the perpendicular distance from D to tangent point C. So now how can we calculate this distance? So we can calculate this distance by using this theorem too. So the deviation of any point point B relative to the tangent drawn to the elastic curve. Suppose they are considering point B to the any tangent drawn into the or drawn to the elastic curve at any other point A. So they are indirectly saying that if you want to measure the distance from B to the tangent or perpendicular distance to the another tangent, so is an direction perpendicular to the original position of the beam. So this is the beam, so this is in a perpendicular directions to the beam. Am I right?
Yes, sir.
So what does it mean? So till now they said this is T B by A. So T B by A equals to the product of 1 by EI multiplied, right? So multiplied 1 by EI multiplied by the number of area about B of the part of the moment diagram between A and B. So they are saying that by the moment of an area about B. About B means what? X bar B, from the B point distance to the, from B to CG point distance, that part of the movement diagram between points A and B. So that's why you can see that the formula we can write for this T B by A equals to 1 by EI area, right? And they are considering the about B because we are getting the value from point B. So that's why we will consider the CG value from point B. Okay. So we are multiplying the X by B. Now similarly, if you want to calculate this T A by B, so the only change is that would be about A point. That time you will consider the distance of X bar is from point A. So that is A by B equals to 1 by EI multiplied with area of AB. Have a look, both the cases area remains same. Why? because both the cases you consider the between A to B, right? Okay, so then both the cases area remains same, only change is x bar A, because we are calculating the vertical or perpendicular distance from point A of the elastic curve. So now if I say to develop the formula for Td by C, right, if I say that, okay, develop a formula for Td by C. So what would be this formula? Who can tell me? Td by C. Okay, so it should be 1 by EI, right? And then area. So area of DC, area of CD or DC, whatever it is, right? And x bar D. Okay, so that time we'll consider the whole area. We'll consider the whole area, and your now question is that, sir, we are looking for deflection, but we are calculating the distance from the elastic curve to the tangent point. What is the use of this value? All right, so that might be the question you might have right now. Just to clarify yourself, suppose this is the beam. Okay, maybe you have the elastic curve is like that. Okay, so you consider one point here, you consider one point here. So this is your C point, this is your D point. But I want to know the deflection of point B, that is your del B, right? I want to know the deflection of point B. How can you draw this, or how can you find this? So now if I draw the tangent from point C, right? If I draw the tangent from point B, right? So here you can see that you can calculate this T D by C, right? And what would be this distance? Who can tell me? This distance would be what? If you consider this is point B, that would be B by C. So we can find out T B by C if you consider the one point at point B, right? But now still we don't know the value of del B. Still we don't know the value of del B, which is our main target. So can you find this del B? If you know this T B by C and T D by C, yes, the answer is yes. How? By using the simple similar triangle formula. Have a look. This is your T D by C, right? So we at least understand that by using this theorem we can calculate this T value, right? So this is the point B, where up to this is maybe T B by C, and we are left to calculate this value only, which is del B. Am I right? So if I consider this total distance is x, just for an example, if I consider total distance is x, right, and this distance is y from C to B, suppose C to B is y, So now can you consider the similar triangle formula? What we can do here, we can consider that T d by C, we can consider T d by C divided by x equals to the simple trigonometry equals to what? Del B plus T B by C divided by what? Divided by y. So now have a look. You know every single details except del B, right? You don't know what is del B, but you know you can calculate T d by C. You can calculate, you know already x, you know already y, and you can also calculate T b by C. So what is the unknown here? Del B. So now you can see the beauty of this formula. So now simply we can calculate del B. That would be easy for us. Okay, so that's why by using this theorem 2 we can calculate the deflection, and by using this theorem 1 we can calculate the slope of the curvature or slope of the elastic curve. Have a look. If you have tangent like this, if you have the curve like this, okay, if the deflection is below the neutral axis, so that time you will have this kind of shape. So that time you consider this is plus, right, and this deflection is also in plus. Okay, but if you find beam is deflecting upward, okay, if the deflection is above the neutral axis, so that time you consider this is negative slope and this is negative deflection. Okay, so measure from the left tangent if theta is counterclockwise. So usually from the left tangent, you consider from the left tangent. If theta is counterclockwise, okay, the change of slope is positive. If clockwise, negative. So have a look, change is counterclockwise. From here you are going anti-clockwise, and from here you are coming clockwise. Okay, and the deviation at any point is positive if the point lies above the tangent. So this is the tangent and point lies above the tangent. So B point is above the tangent, so this is plus. Negative if the point is below the tangent. So I will look, this is the tangent and this is the B point is below the tangent, so that is negative. So based on the tangent location they consider the plus and minus. Okay, so this plus and minus doesn't mean that your deflection is minus or rotation is minus. It mean the directions. Keep in mind, right? Distance cannot be minus. Distance minus means what? It's the direction, opposite direction. So here you might need some shortcut formula, because now I consider yourself as an expert on this shear force and bending moment diagram. So here are some shortcut to calculate the moment diagram. Okay, suppose just for an example, if you consider that you have a simply supported beam and you are having a, suppose you are having a load like this, so that time you know your beam diagram, or sorry, BMD diagram would be like this. You understand? So how to calculate this area? You can find it, right? You can find this one and you can find this is one options and this is another options. Okay, so if you know this one, you can use the trigonometry formula to calculate the area of this moment diagram. Area of moment diagram, keep in mind, not area of shear force diagram. The area of load can be used to the area, to the value of shear force diagram. The area of shear force diagram can be used to the drawing of moment diagram. So now area of moment diagram we are using in the calculation of deflection. So to skip this kind of detailed explanation or calculations, we can use some shortcut here. So if you find you have a loading type is coupling loading, right, which is generating the moment. Okay, and this is a fixed support. So that time you have this kind of formula for area of this moment. So here you can see, if you find another type of loading, that is the point load or concentrated load. So on that particular point, you'll find the moment diagram is look like a rectangular. As you see, if it is a point load, the moment diagram is look like a rectangular. Suppose you have this similar situation, you have a fixed support one end and another end is point load. So that time your moment diagram will be look like that. So you know this distance is L, right? And that would be H. Okay, so this would be the area half BH. Okay, sorry, that should not be half, this should be 1 by 1 BH. Okay, I will come to another shortcut formula here, how to consider these two formula without doing this kind of details calculations. There is a shortcut. I'll come later once you understand this. So this one is 1 by 3 BH. Okay, so this is the X bar from point B. Keep in mind, from point this base, this is X bar, 1/3 of B. But if you come from here, it would be 2/3 of B. Do you understand? Okay. So if you get uniformly distributed load, that time you have second degree, right? In the moment diagram, line of action will be second degree, and your equation would be 1 by 3 BH. Area of this is the approximate values, you understand? So now this shortcut you can also use for your complex movement diagram technique, SFD BMD technique. That will give you approximate result, not accurate, but it will help you to find out the result faster than complex technique. So 1/3 of BH, and that would be 1/4 of B. Okay, and if it is uniformly varying load, so that time you are having moment diagram as a third degree, so that time it would be 1 by 4 BH and 1 by 5 B. So now have a look, if you consider this area and X bar formulation, you will get an interesting thing here. What is that? Every time is BH is common here, right? So BH is common for this formula for area, right? And B is common for this each formula, right? So we can correlate this formula with respect to the degree of line of action. So if you consider the moment degree, have a look, this is first degree, but it is 1 by 2. This is 0 degree, it is 1 by 1. So what does it mean? If I consider degree as a n, degree as a n, n is 0, n is 1, n is 2, n is 3, right? So what I can say here, this is 1 by n plus 1 into this. Okay, but for this one I can say 1 by n plus 2 into B, because have a look, you can consider 1 by n plus 2, so n is what? 0, so that's why n plus 2 means what? 2. So either you can follow this formula, 1 by n plus 1 BH for the area, and 1 by n plus 2 into B is for the X bar. But keep in mind, this X bar distance started from the base. So simply if you find this is 1 by 5 B what should be this distance? 1 minus 1 by 5b, right? This is simple mathematics. So if you understand up to now, so that means majority of the theory is done. I hope you can see now, right? If you want to find point B deflection or the beam deflection at point B, that is del B, whatever you like to say. So that time we can do this simple technique. First of all, we can compute the value of TC by A. If it is A, this is B and this is C. So that time we can calculate the TC by A. Okay. And then we can calculate the TB by A. So TB by A means this distance, right? So if I consider this BD equals to, we can say what? Del plus T B by A, right? Okay. So similar way we can say that del equals to BD minus T B by A. Okay. So both are similar. So by similar triangle technique, we can calculate this BD because del plus TB by A equals to BD. So since if you know this TC by A, L, X, you can calculate TB by D. So once you can calculate B by D from the similar triangle formula, so that time we know this is del plus this, and if you know this BD, you can calculate this del easily. So that is the simple technique as it is. So now look into a problem. The problem is like this. You have a simply supported beam. You have a simply supported beam. Okay. Concentrated load at 300 Newton at 2 meter distance. Suppose you have a load at 300 Newton at 2 meter distance. So since it is simply supported, there will be one reaction and there will be another reaction. So this is 2 meter, 1 meter, 1 meter, 2 meter, and total is 3 meter. So they want to compute the value of EI del, indirectly del value, right? Which is 1 meter from the left support. So ultimately point B. At point B, they want to calculate the deflection. Do you understand that?
Sir, can you please repeat again? I have missed that part because of buffering.
So in this problem, they have assigned the load at 2 meter distance from the left support. Okay, left support means point A. Okay, but they want to know the deflection at point B, which is 1 meter distance from the left support A. Okay, so now what we can do, we can draw the tangent. So first of all, since we are going to use the similar triangle formula, so you can consider one tangent point at A, another point at C, another point at B. Now if you draw the tangent at point A, you will find you can easily calculate the value of TC by A. So before that, the general situation is like that you have to calculate the reactions R1, R2. Okay, so in this technique there is a way that you cannot combine several loading to draw the moment diagram. Suppose in a beam you might have like different kinds of loading. Maybe you have UDL and point load. Maybe you have UDL and point load, right? So we know while we draw the moment diagram, that moment diagram is combined. We don't know what will be the degree of actions, and we don't want to get this kind of complex situations. So that's why what we will do, we'll try to draw separately the moment diagram for individual force. So what is the first force here? Reaction force, right? 100. Another force is 200. another force is 300. So there are 3 individual forces are here. So that's why we'll try to draw the reaction diagram based on these individual forces. What will be the moment diagram? Because this is the point load. In SFD this would be the 0 degree line of action, right, due to the point load. In BMD it would be inclined. So if you consider this reaction force 100, so this is acting here, right? So now consider a beam which is acting here as a 100, and if you come up to this section, if you take a section at point B, what will the reaction, what will the moment in this section? 1 into 100, 100. If you take a section here, it would be 2 into 100, 200. If you take a section just before C, it would be 3 into 100. There would be 300, because 3 into 100. So this is for reaction 1. So the drawing of this reaction 1 will be like this, inclined. Now, since you are taking section for which section, which point? At point just before C. You are taking the moment for just before C. Do you understand? So again, if you take a section, you finish this one, you have another load. What is that? 300. So this 300 is acting downward, right? So it will generate actually anti-clockwise movement. So 1 plus 300, how much? 300, right?
301
minus 300. So it is going minus 300. So keep in mind, in the section point you should have a balance. Plus 300, minus 300. Actually it comes to the 0. So what you did, you just take a section here. You understand? So if you take a section, and what is the situation? The beam situation is like this. So first of all, you consider the beam, which is 100 Newton load acting upward. So first of all, you consider this beam is only having this load, and you are drawing the moment diagram here. Okay, so what is that? 100 into 3. So that would be like this, 300. Now you introduce another. Now you do not consider this one. You forget about this. Now you have load 300 Newton acting downward. So this acting downward, and this distance is 1 meter, right? So 1 meter into 300. 300. This. So this is minus 300, and this is plus 300. So our section is okay. That means what? At this section we find the equilibrium. So that was, I mentioned that you have to draw the moment diagram for individual load. That is the trickiest part in this area moment calculation or moment area method. Once you can draw this one, rest of the things is easy. Up to this is clear or not? Let me know.
So the load 300, applied load. So that part will you explain again?
So this is 300, right? So while you consider this 300, your beam will be look like this, right? So only this 300 load. So 300 load is acting downward with respect to this point C, or just before C. It is rotating counterclockwise.
Yes, sir.
So rotating counterclockwise. So it is rotating counterclockwise negative. So distance is 1. So load is 300 and distance is 1. What will be the moment at point C? 1 into 300, 300, and counterclockwise minus. So ultimately, if you take the summation of these 2 points, or summation at point C, plus 300 minus 300, 0. As you know, if you take a section, the equilibrium should be maintained. Okay. So once you understand this part, then your life is become very easy for this problem. So first of all, we target to calculate this del B. So we know by using the similar triangular technique that I have discussed here. By similar triangular technique, we can find out this del B. So for that, we need T C by A and T B by A. Okay. So just use the formula T C by A and T B by A. Okay, as it is. We know formula T C by A is like this. Now the question is the area of CA and area of X bar C. Why X bar C? Why not X bar A? Do you understand that? Because you are calculating the distance from the tangent point, from the point C to tangent line. Do you understand why X bar C? If you look back to the formula that we have discussed. Here you can see, right? While you consider the tangent distance from B, we consider X bar B. While you consider tangent distance from A, we consider the X bar A. I hope you understand. Now try to put the area formula. So since it is above the neutral axis, it is plus moment. This is below the neutral axis, should be negative moment. So area should be plus and minus, similar way. So now we look 300. You remember the formula for area, 1 by n plus 1 into BH, right? And for the X bar, 1 by n plus 2 into B, right? If you look from the base. Okay, so now this is what degree line of action? First.
1, sir.
Right? The line of action is first. This is also same. First degree, right? Okay. Now we can see 1 by n plus 1 means 1 by 2 BH. So you can consider this is your B. How much? B is 3, H is 300. So that's why 1 by 2, B is 3, H is 300. Up to this is clear from the formula. Then here you don't have to use the formula because you know this is simply triangular shape. For triangular shape, you can consider half into base into height. But while you will have UVL or UDL, so that time you might need to use this kind of formula. Otherwise, you can easily find out this. Okay, so let me complete this one first. So we can calculate this for area and this for X bar. Okay, so 1/3 of 3. Total distance is 3. So from here, the CG point should be here. 1/3 of 3. You understand? From the base. Or you can also use the formula 1 by n plus 2 plus into B. So n is 1, so 1 by 3 into B. B is 3. Same, right? Similar way, now come to this part. So this part, 1 is the B. B is your 1. And H is similar, 300. So 1 into 300 divided by 2 into 1 by 3 into 1. This is your area and this is your X bar. Because according to the formula, we need to calculate the area and X bar. So once you know this, okay, you find TC by A equals to 400 by EI. Okay, that's good. We calculate the TC by A already. Now, what else we need to calculate? TB by A. So similar way, we can calculate TB by A. Here is the challenge of area. For TB by A, what would be your considered area? Who can tell me? For TB by A, area should be between A to B.
Yes, sir.
Yes,
So
sir.
that is your considered area. So on that case, you have, this is first degree, right? So n would be 1.
Yes,
So
sir.
you can use formula 1 into 100. This h is 100 divided by 2. And base which from where you will consider the base? From A or B? Centroid should be from B, because this is TB by A. Because this is TB by A. So distance should be from B. So from B to the CG point of this would be 1/3 of this one. 1/3 of this one. Okay. So now have a look. You got value of TB by A, TC by A. Up to this is clear. So similarly, use the triangular formulation. You know that you can write BD. You can write BD by 1, which is X, and TC by L, which is how much? Similar triangle formula. So here you can write like this: BD by 1, okay, equals to CE or TC by A, same, divided by 3. Now you know the value of TC by A. What is that? 400 by
400 by EI.
EI. And you know the value of BD, which is del plus T B by A. So now you put the value of del. What is T B by A? 100. So here you can see T B by A is 100 by 6 EI. So what else you need here? BD. You can calculate the BD from this one, because you know this one, you know this one, you know this one. So you can consider BD equals to this by this, right? 1 by 3 into 400 by EI. Now put the value of BD here: 1 by 3, 400 by EI. Now have a look. Everything is known to you, only del. So now you can easily calculate the value of del. Okay. So have a look. They calculate the del, which is EI del equals to 116.7 Newton meter. So now if you know the value of EI, you can say del equals to, it should be in meter, right? So as simple as it is. So now you have to be expert on this movement diagram, nothing else, because theorem of these techniques are very easy. Okay. So similar way here, if they do not mention that where you need to find out the maximum or where you need to find out the del, or if they said you have to find out the del maximum, because in this particular problem they said calculate the del at location 1 meter. So that's why you consider point B. But if they say that you have to find out the maximum deflection and compute the maximum EI del. Okay, so what you will do? Similar technique you will follow that we use for the what? Double integration method. So if you use the same problem, right? If you use the same problem and you consider random point B at distance of x, because you don't know the value of x, where you will get the value of del maximum, that is the distance of your x. Do you understand? Previously it was defined the value of x or value of b was 1 meter, but in this problem they do not
Yes, sir.
mention, so the problem remains same. So here you can easily calculate the values tb by a, right? In the previous calculation x was x was 1. Do you remember?
Yes, sir.
Right? But here you keep this x as a variable, because you don't know the value of x. Why you don't know? Because you don't know the location of maximum deflection point. That's why you are keeping that, or you are assuming that the maximum deflection is at the location of x. Okay, and rest of the process is similar. Now you get t b by a is 100 x cube by 6 ei, but whereas in the previous problem you got 100 ei for this t b by a. Do you remember? So have a look. If you put the value of x is 1, it remains same. Do you understand the equations?
Yes, sir.
Okay, but we want to put this value of x where is del is maximum. That's why that is the challenge. You don't know the value of x. So now we are still keeping the x as a x. Now we can calculate the tc by a. So in case of calculation of tc by a, we don't have to use x variable, because we know the total distance is 3, right? So that's why we can easily calculate the tc by a easily. So now for this situation, you already know the like previous one, tc by a, and that would be your bd, where this is your del max, but you don't know what is your bd. But similar way you can consider, because you know this tb by a, you can develop an equation with respect to the x. So if you consider
Yes, sir.
bd equals to bd divided by x equals to tc by a divided by what? L is 3. So here you can see bd equals to x by 3 into tc by a. So that is that. So you know tc by a, so you put the value of tc by a, you finally get the bd value is 400x 3 ei. So now challenge is that what would be the value of x. So I hope we can use the similar technique that we used to use in the double integration technique. So we know that del should be bd minus tb by a. That's for sure, right? From this equation, if total is bd and this is del and this is tb by a, so del should be bd minus tb by a. You can get an equation like that, where only x is unknown, right? This is valid for any position between left reaction to the load, because we consider here x is from point A to point, this distance we are assuming this is the distance of x, somewhere of this between these two distance. Okay, so we are first of all we consider that since we consider this 300 is this locations, and we know we must have a chance to get the slope between these, so we consider this distance is x. So now if you consider differentiation of these equations, Okay, so we get dEI by d del by dx, right? So if you do the differentiation of this term and this term, so you will get 400 by 3 and you will get 300 x square by 6. Okay, I hope this is simple differentiation you consider. Now the challenge is that how can you find the value of x? Because we know where the deflection will be maximum. Where deflection will be the maximum, there dl by dx should be 0. Do you remember from the double integration technique we used to discuss like that? Like curvature or slope of the equation should be 0. Like slope would be like straight line or tangent would be like a straight line. So if you consider this term is 0, now have a look. You can write 400 by 3 minus 300 x square equals to divided by 6 equals to 0. So from these equations you can get the value of x. You will get the value of two values of x. So you'll find the most relevant value between the 1 to 3, because 300 load is given between 1 to 2. Okay, so they find the distance is 1.63. So now if you put the value of 1.63 in this equation, if you put the value of 1.63, what does it mean? The location of x here, you can get the value of EI del. Okay, so if EI del is given, you can get the value. Okay, so at the point or the beam will have maximum deflection 144 divided by EI. That is the maximum deflection this beam can show. So now we can calculate the deflection in meter parameter by putting the value of EI. So please try to practice this